So I'm re-recording this because the Zoom session that I did with my students today got corrupted and I couldn't save the video, so I'm going to go over what I went over with them today again in this video. And when I talked to the other geometry teachers, we discussed that there were lots of questions pertaining to the Delta Math 11.3, 11.2, 11.3 homework, and there were a few questions also pertaining to the activity that we did today, so that's what I'm going to go over. The first one here is a certain Algebra 2 class of 26 students. In a certain Algebra 2 class of 26 students, 18 of them play basketball and 7 of them play baseball. There are 5 students who play neither sport. What is the probability that a student chosen randomly from the class plays both basketball and baseball? So the first thing I need to determine is what kind of question is being asked of me here. And at the end here it says, what is the probability that a student chosen randomly from the class plays both basketball and baseball? So that's our probability. Basketball and baseball, remember that's our and symbol. And so what we're really looking for here is how do the two basketball and baseball overlap? So we're going to use a Venn diagram to solve this problem, but before we do that, we're going to talk through some of the elements of this problem. So we have 26 total students, but here it says there are 5 students who don't play a sport, no sport at all. So we got to figure out how many do play a sport. So 21 of the students, when we subtract the 5 from the 26, we get 21 of the students play a sport. Then it says 18 of those 21 and 7 of them play baseball. So let's add the 18 to the 7. That's 25. Now we can figure out how many of them play 2 sports, right? So we're going to take the 25 and we're going to subtract the 21 from it. That's our overlap right there. When we subtract the total that were on both teams from the total that actually played a sport. So when we do that, then we're going to make a Venn diagram. So we're going to put basketball players in one oval and baseball players in the other. Outside of those 2 ovals, we're going to put the number that didn't play a sport at all. So that's going to be our 5. Then we're going to put our overlap right here where the 4, this is where the 4 goes because that's the ones that played both. Then to figure out how many go over here, we know that there were a total of 18, so we're going to subtract the 4 from the 18, and that's going to give us 14 over here. And then over here it says we have 7 that played baseball, so we're going to subtract the 4 from the 7, and that gives us 3 here. So this question is really just asking us about the overlap, because it's asking us how many played both. So that's going to be our 4, and we're going to put that 4 over that 26. So when we're looking for the probability of who played basketball and baseball, we put the 4 over the 26. That reduces to be 2 over 13, which is 0.154, which is 15.4%. So on the second problem, it says in a certain Algebra 2 class of 27 students, 18 of them play basketball and 16 of them play baseball. There are 3 students who play neither sport. What is the probability that a student chosen randomly from the class plays basketball or baseball? So here again, we're going to look at how many didn't play a sport. There were 3 out of the 27. So we're going to subtract, and oh, by the way, this is the other thing. We're looking this time for the probability of basketball or baseball. So that's going to be a little bit different in the way that we work that. So we're going to use a Venn diagram again, and we're going to talk through that. So we're going to subtract the 3 from the 27 again, because 3 students didn't play a sport at all. So that gives us 24 that played a sport of the 27. Then we want to know how many total played one or the other. So we're going to do the 18 plus the 16 again. That's going to give us 34. So hopefully you remember what we're going to do with these 2 numbers. We're going to subtract the 24 from the 34 to find out how many played both sports. So that gives us 10. So here again we're going to draw a box, and we're going to do an oval with basketball and an oval with baseball. We need to indicate how many students didn't play a sport at all. So that would be our 3. So we're going to put that up here. And then how many played both? That's going to go here. That would be 10. So if this was an and statement, our answer would be 10 over 27. But this is an or statement. So what we're going to look for now is how many played, how many are in both circles. And so ultimately what we're going to do is add together all of these numbers. So we have 18 that played basketball. So this whole circle here has to equal 18. So we're going to subtract 10 from 18. That's going to give us 8. 16 played baseball. So we're going to subtract 10 from 16. That gives us 6. So ultimately what we could do is 2 ways we could solve this. We could add these 3 numbers together, which will give us 24. Or we can do our typical probability for an or statement, which means we're going to add the 18, all of the basketball players, 18 over 27, plus the baseball players, 16 over 27, and then we're going to subtract the overlap, which is the 10 over 27. So that's what I did down here. I added the 18, the total basketball players. I added to it the total baseball players, and then I subtracted the overlap. That got me 24 over 27, which reduces to be 8 over 9, which is 0.888 or 88.9%. The next problem that I was having questions about was the spinner questions. So this one says there's a spinner with 15 equal areas, numbered 1 through 15, and if the spinner spun one time, what is the probability that the result is a multiple of 2 and a multiple of 5? So once again, I'm going to write my probability statement first, probability of multiple of 2 and a multiple of 5. This time, I'm going to go ahead and write out 1 through 15. I like doing this problem visually because I think it's a little bit easier for me to understand. Maybe you too, so we'll see how you guys do on this one. So first it's asking us for multiples of 2. So I'm going to go ahead and circle all my multiples of 2, 2, 4, 6, 8, 10, 12, 14, right? Then it's asking me for the multiple of 5, okay? So we've got the multiples of 5. There's 5, 10, and 15. So what we want to do now is we want to talk about how many of these were a multiple of 2. So we got our red circles, 1, 2, 3, 4, 5, 6, 7. So that's 7 over the 15, right? Now the question is, of those 7, how many of those were multiples of 5? Only one of them, right? So this is the one that has both a circle and a square. So when we do this problem, we're going to do 7 over 15 times our 1 over 7. Now notice, because again, we were talking about of the 7 of the circles, how many of those have squares? Only one of them. So this is a conditional, right? So we're going to do 7 over 15 times the 1 over 7. That would have been 7 over, let's see if I 7 times 15. That would have been 7 over 105. But this is what I know, y'all. Those two 7s cancel each other out. That's why I got 1 over 15 here, which is 0.067, which is 6.7%. All right, let's look at this next one. There's a spinner with 13 equal areas, numbered 1 through 13. If the spinner is spun one time, what is the probability that the result is a multiple of 4 or a multiple of 3? So once again, I'm going to write my probability. This is an or statement. So this is a multiple of 4 or a multiple of 3. Now this is when we add. We're not looking for overlap here, although we are going to use the overlap. And we're going to subtract it because this is an or statement. So we're going to add our two probabilities together, and then we're going to subtract the overlap. So this time, again, I did 1 through 13. We're looking for multiples of 4. So that would be 4, 8, and 12. So that's 3 out of the 13. And then we're looking for multiples of 3. That would be 3, 6, 9, and 12. So that would be 4 over 13. Now, how many of them have both the circle and the square? One of them, right? That's the 12 right here. So we're going to do a 4 over 13 plus the 3 over 13, and then we're going to subtract the overlap, the one that's both of them. That's going to give me 6 over 13, which is 0.462, which is 46.2%. All right, so here's our next one. These are the ones that talked about symbols. So this is given that the probability of A is 0.75% or 0.75, probability of B is 0.62, and the probability of A given B is 0.95. Find the value of the probability of A and B, rounding to the nearest thousandths if necessary. So here's the formula that you guys got to know. What is the probability of A given that B occurred? That's what that slash means. What is the probability of A given that B occurred? It is the probability of A and B divided by the probability of B. So whatever this is right here, this B, that's what you're always going to divide by, okay? If this said the probability of B given A, we would still do the probability of A and B, but we would divide it by the probability of A. So now all we have to do is populate this formula, right? So we've got the probability of A given B is 0.95. We're going to actually find the probability of A and B, and we're going to divide by the probability of B. So what's the opposite of division, y'all? It's multiplication, right? So we're going to multiply both sides by this 0.625. That's what I did here. Multiply 0.625 by both sides. That's what's going to cancel it out here. That's going to give me 0.625 times 0.95. So the probability of A and B is 0.589, which is 58.9%. All right, let's look at our next one. This one says given the probability of A is 0.5 and the probability of B is 0.26, and the probability of A and B is 0.22, find the value of probability of A or B. Now remember, when we're talking about A or B, we're going to add the two individual probabilities. We're going to subtract the overlap. Here's our probability of A, that's an individual probability. Probability of B, individual. So we're going to add those two numbers together, and then we're going to subtract our AND statement from it. So the probability of A or B, which is what it asked us, remember this is our OR symbol, is the probability of A plus the probability of B minus the overlap, right? That's what the probability of A and B are. So all we have to do now is sub in these numbers, 0.5, 0.26, 0.22, and we get 0.54, which is 54%. And this is on the formula sheet, y'all. So that formula is on the formula sheet. So this one says, given that events A and B are independent, with the probability of A being 0.89 and the probability of A and B being 0.534, determine the value of probability of B rounding to the nearest thousandths if necessary. So this word right here, independent, is really important because that means that it's not a conditional statement. When we had that slash, it was conditional. This one means that one is not dependent on the other. So when we do this one, our formula is going to be the probability of A and B is equal to the probability of A times the probability of B. This too is on the formula sheet, y'all. So all we have to do now is sub in what we have. The probability of A and B is here, so that's going to be 0.534. The probability of A is 0.89. So we sub those in, and remember again, when we have 0.89 here times probability of B, we're going to have to divide both sides by 0.89 to get rid of that 0.89. Cancels out there, so then it's going to be 0.6 is equal to the probability of B, which is 60%. Here's our next one. Given that events A and B are independent, again, with the probability of A being 0.9 and the probability of B given that A has occurred, determine the value of the probability of B rounding to the nearest thousandths, if necessary. Okay, so here we go. So events A and B are independent. This again is really important here. So we know that B it says, what is the probability of B given that A has occurred, okay? So the way we do this is the probability of B given A is equal to the probability of B, and I'm going to tell you why, okay? This is the way this works. The probability of B given A is the probability of A and B divided by the probability of A. Why? Because this probability of A means that has occurred. What is the probability of A and B? It's the probability of A times the probability of B, right? So what's going to happen here, if we have a probability of A on the top up here and on the bottom, aren't they going to cancel each other out? So, yes. So that means that it's just the probability of B, because these two right here, this probability of A and that probability of A would cancel each other out. We're only left with the probability of B. So if this was flipped, y'all, and it said the probability of A given B occurred, then we'd have to have probability of B on the bottom, right? And we would be left with the probability of A. So here's our next one. If you select one card, so this one is from that mutually exclusive inclusive sheet on one of the pages is that one, and then the second page is independent dependent. So we're going to talk about these questions too from that activity. So this is, if you select one card from a 52 card deck, what is the probability that you choose a red 7 or a black 8? So the first question we want to ask here is this a mutually exclusive or an inclusive event? Well, we only pulled one card, y'all. It is an OR statement, and that's what tells us whether it's inclusive or mutually exclusive, right? But we only pulled one card. So this is our statement, the probability of red 7 or green or black 8. Yeah, I can't read today. these are mutually exclusive. The reason is because only one card was chosen, right? So the probability that we pull a red 7, there are 2 7s that are red, and there are 2 8s that are black, right? So all we're doing here is adding these together, because remember, when it's an OR statement, we're going to add. The only time we're going to subtract is if there's some overlap. And there is no overlap here because we only pulled one card. So this is going to be 4 over 52, which reduces to be 1 over 13, which we could also say is 7.7%. It would be 0.077. Okay, so the next one that I want to go over is if you select one card from a 52 card deck, what is the probability you chose a 5 or a black card? Okay, so this is again an OR statement. Now, I would have got a question for you. Are there any 5s that are black cards? The answer is yes, you're right. So that means this is going to be an inclusive statement, right? And that's because there is going to be overlap. There are 5s that are black. So what we're going to do is there are 4 5s in the deck, right? And there are 26 black cards. How many of those black cards are 5s, or how many 5s are black cards? That's going to be our overlap, because right now those 2 5s are here and those 2 5s are here, and we can't have them represented in both groups. So we got to subtract the 2 over 52 because that's how many are both black and 5s. So when we do this, we get 30 over 52 minus 2, that's 28 over 52. That reduces to be 7 over 13, which is 0.538, which would turn out to be 53.8%. Okay, now we're on the back, or the independent-dependent questions. So this says Mrs. Vanderpump's class contains 13 girls and 17 boys. Mrs. Vanderpump needs to select volunteers to pass out papers. She randomly selects one student and then selects another student from the class. Find the probability that she chooses a girl first and then a boy. So my first question for you here is this going to be independent or dependent? So if she chooses one and then chooses another one, obviously we started out with how many students? 13 plus 17, that's 30, right? So if I chose one, how many do I have left? 29, right? So this is going to be a dependent probability. We're going to find the probability that it's a girl and a boy. Notice it has the and word here. Girl first and then boy, right? So they are dependent. Why? Because once I choose a girl, there's only going to be 29 students left, right? So that's why the number of students is going to decrease, right? So we're going to do 13 over 30. That's how many girls there were, but there are still 17 boys, right? But there's only 29 students left. So we're going to multiply across the top, and we're going to multiply across the bottom, and we get 221 over 870. And then that would be 0.254 or 25.4%. All right, here's our next one. Find the probability of Taylor rolling a 1 on a number cube and then rolling a 3 on her second roll. So here's my question for you. If I roll this dice, the same cube, if I roll it twice, does what I do first affect what I do second? The answer to that question is no, right? So we're looking here again for the probability of rolling a 1 and, notice that and word, and a 3, okay? So they are independent because rolling the dice the first time does not affect what I do the second time. Okay, so rolling a 1, there's 1 out of 6 that's a 1, and there's 3 out of 6 that's a 3, right? I mean, it'd be great if I could talk. 1 out of the 6 sides is a 1, and 1 out of the 6 sides is a 3. So we're going to multiply 1 over 6 times 1 over 6, that's 1 over 36. And again, when we turn this into a decimal, it's 0.028, which is 2.8%. Here's our last one. This one was a little tricky, so I kind of wanted to go over this with y'all. Gigi's making a necklace with a bag of 50 beads. 10 red, 25 white, 5 yellow, 8 blue, and 2 green. Find the probability of the first 5 beads of the necklace to be white, yellow, green, white, and red consecutively. That means they got to be in this order, y'all. So let's talk about what's happening here. So what are we really looking for? We're looking for the probability that we get white and yellow and green and white and red in that order. We have a bag of 50 beads. That's going to be our denominator, right? That 50, at least as we start, because we're going to take beads out and we're not going to put them back. So what's going to happen to these numbers every time, the denominator number, every time we pull another bead out of the bag? The number's going to decrease, isn't it? Okay, so this is going to be a dependent problem because we're continuing to take beads out of the bag, so the numbers are going to keep decreasing, right? So we have 25 white beads, so we're going to put that 25 over the 50. Then it says yellow, and we have 5 yellow, but remember, we kept that bead, right? So there's only 49 beads left in the bag. Then we have green. There were 2 green. See up here, 2 green. So that's going to be 2, again, over 48 because we got 2 beads out of the bag now. Then we've got white again. Now, wait a minute. I already used a white bead, so there's not 25 white beads in the bag now. There's only 24. And that's going to go over the 47. Again, these numbers are decreasing in the denominator as well. And then the last one was red, and we still have 10 red beads in the bag, so that's 10, and again this number goes down to 46. So then we multiply all these numbers across the top, we put that on top, we multiply all these numbers across the bottom, and that's our denominator. So when I do this in the calculator, I would divide the 60,000 by this 254,251,200. That would reduce to be 54 over 210, and that's 0.00024. And remember here, we're moving our decimal 2 places to the right to turn it into a percentage. So this would be 0.024%. This was a pretty tricky problem. I definitely agree, but it's a good one for us to go over. So hopefully this helps you guys.